It is section 4.5, Indeterminate forms and LHopitals rule. In this section, we'll study a special technique called LHopitals rule, which will be very useful for the computation of limits. Okay, let's begin with definitions of indeterminate forms. Consider a limit of the form limit as x approaches a, f of x over g of x. If both f of x and g of x approach 0 as x approaches a, then we call it an indeterminate form of type 0 over 0. If both f of x and g of x approach infinity, then we call it an indeterminate form of type infinity over infinity. Here, we are interested in these two types. Okay, here we have LHopitals rule. Sometimes it is called Bernoulli's rule. Here we consider a limit of the form. Now we consider two cases, both f of x and g of x approach 0, or both f of x and g of x approach infinity or minus infinity. In this case, one of them can go infinity and the other one can go minus infinity. But for this case, we call it a type 0 over 0 or 0 over 0 shape. Now, for this case, we call it infinity over infinity, or infinity over infinity shape. Then we can get the limit along with this formula. You differentiate f and g separately and take a ratio and limit. So that's a LHopitals rule. And after the differentiation separately, again, it can be 0 over 0 or infinity over infinite. Then you can apply one more time LHopitals rule. So sometimes you're applying in several times of LHopitals rule. And here, either the numerator or the denominator has a finite non-zero limit, then you cannot use LHopitals rule. Okay, in this rule, here, a can be any finite number, and also it can be infinity or minus infinity. We'll see details with examples. Okay, here, use LHopitals rule to evaluate the limit, and we'll try to compare the result along with the traditional methods studied in chapter 2. Okay, limit x approaches minus 2, then now the numerator approaches 0 and also denominator approaches 0. So this is type 0 over 0. Now here, by using traditional technique, we can do in this way. The given term is same as limit, and x approaches minus 2. And now there is x plus 2. And here we can factor out. So it's x plus 2 and x minus 2. So we can cancel x plus 2 so that that is the same as the same limit and 1 over x minus 2. X is approaching minus 2 so that we can get here 1 over minus 4. Okay. Now we'll try to use LHopitals rule as 0 over 0 shape. So the given term is same as the limit, and now derivative of x plus 2 is 1, and divided by, here, derivative of x squared minus 4 is 2x. Now, here x is approaching minus 2, so that will be 1 over minus 4. So we can get the same result. Okay, for that one, again, let's do it by using the traditional method. Here, that is quadratic polynomial on the top, and on the bottom is again quadratic. So that by dividing by here x squared, bottom and top, we can simplify the computation quite easily. Anyway, in the beginning, top and bottom are approaching infinity, so it is an infinite over infinite shape. So here the given term is same as limit, the same limit, and x squared divided by x squared, then that's a 5 and minus 3 over x, and that is here now 7 plus 1 over x squared. As x approaches infinity, this term will convert the approach to 0, and this term again will approach to 0, so that here the result will be 5 over 7. Okay. Now this is infinite over infinite form, so that we can use LHopitals rule. So the given term is same as a limit, and here we are differentiating bottom and top separately. That is 10x minus 3, and that is 14x. Okay, as x approaches infinity, again, this is infinity over infinity shape, so that here we can apply the LHopitals rule one more time, and the derivative of top will be 10, and derivative of bottom will be 14, so that is same as now 5 over 7, which is the same as earlier result. Okay. Okay, now we'll use LHopitals rule to find the limit. Okay, and as t approaches 0, now top is approaching 0, and also bottom approaches 0. So it is a 0 over 0 shape. So by using LHopitals rule, it is the same as the limit derivative of sine 5t is same as cosine 5t, and times now 5 divided by 2. Now here, as t approaches 0, now cosine 5t will approach 1, so that the answer must be 5 over 2. Quite simple. If we try to find the limit by using the traditional method, then it's given in this way. Here, the given term is same as limit t goes to 0, and now sine and 5t, and divided by 5t. And to make it the same, we have to put over there 5 and 2. Right? Then we know that as t approaches 0, sine 5t divided by 5t, okay, this is x, and you get the same x, sine x divided by x. As x approaches 0, the value is approaching 1, so that here we have 5 over 2, the same answer, right? Okay, now here theta approaches 0, then top approaches 0, and again bottom approaches 0. So we can use LHopitals rule. So it is the same as the same limit, and cosine derivative as minus sine theta, and divided by e to the theta is derivative is same as itself, and minus 1. As theta approaches 0, top is approaching 0 and bottom again approaches 0. So that again we can use the LHopitals rule. That is now minus cosine theta, and bottom is now e to the theta. So that is approaching 1, so the minus 1 divided by 1, so that here minus 1 divided by 1, which is minus 1. So that is final answer. Okay, let's go to C. Here, once x approaches 0, then now top approaches 0, and again the bottom approaches 0. That is 0 over 0 shape. So we can use LHopitals rule. That is same as limit as x approaches 0 and 1 minus cosine x divided by here 3x squared. Again, as x approaches 0, top will go to 0 and bottom will go to 0. Okay, so we can use one more time LHopitals rule. That is same as limit, and derivative will be now sine of x divided by 6 now x. So we already know that here sine x over x is approaching 1, so that the answer must be 1 over 6. However, now we'll try to use LHopitals rule. Now, and x approaches 0, then 0, and now 6x will approach 0. So that simultaneously 0 over 0. Then here we can use one more time of the LHopitals rule. So that is cosine x divided by 6. As x approaches 0, then it is approaching 1, so that is 1 over 6. So that is the final answer. Okay, now part D, limit x approaches 0 and x 2 to the x. So it is approaching 0 and divided by 2 to the x. If x approaches 0, then 1, so that 1 minus 1 is 0. So that is 0 over 0 shape. So we can use LHopitals rule, same limit, and here derivative by using product rule. That is 2 to the x, now plus x, here 2 to the x, and times logarithm 2, and divided by, here derivative of 2 to the x is same as 2 to the x and logarithm 2, and minus 1 will disappear. And we can simplify this term. That is the same as limit and 2 to the x everywhere, so that we can cancel out. Then 1 plus x logarithm 2 divided by here logarithm 2. So once x is approaching 0, then it will approach 1 over logarithm 2. So that is the final answer. Okay, now we'll try to use the LHopitals rule for other indeterminate forms. Let's begin with here 0 times infinity type, 0 times infinity shape. Okay, here in this term, x squared, as x approaches infinity, it will approach infinity. Now e to the minus x squared, that will approach 0. So it is type infinite times 0, or 0 times infinity. Now the given term can be written in this way. If you want to use LHopitals rule, then it must be fraction, and also both bottom and top should go 0 together, or should approach infinity together. Without that, you cannot use L'Hopital's rule. So you have to manipulate the given term. Okay, here, that is same limit and x cubed divided by e to the x squared. So here, as x approaches infinity, the top is approaching infinity and bottom also is approaching infinity. So it is infinite over infinite shape. So we can use now L'Hopital's rule. Okay, the limit and derivative of x cubed is 3x squared, and derivative of here e to the x squared is same as e to the x squared times 2x. Okay, we can simplify this one a little bit. That's 3x on the top. That is now 2 times e to the x squared. Again, here, as x approaches infinity, it will approach infinity, and now bottom also will approach infinity. Okay, so that is the same as limit. Okay, let's put the coefficient in front of that, and then derivative will be 1, and derivative of e to the x squared is the same as e to the x squared and 2x. Now, as x approaches infinity, the top is 1 and bottom is approaching infinity, so that this term is approaching, whole term is approaching 0, so that is 0. Okay. That means that here e to the x squared is increasing much faster. Okay. Now, for that one, as x approaches 0 from the right, then this will approach 0, but logarithm x will approach minus infinity. So it is a shape of 0 times infinity. For that one, you have to manipulate the given term to get here the fraction and 0 over 0 or infinite over infinity. Okay, let's do in this way. That's the same as limit, the same limit, and then here let's put a logarithm x on the top, on the bottom x to the minus 2. Then it's same as that, right? Then in this case, now logarithm x will approach infinity, and now here the x to the minus 2 will approach infinity. So it is infinity over infinite shape. So here you can use L'Hopital's rule. So it's a limit, and that is 1 over x, and bottom derivative is minus 2 x to the minus 3. Okay, now we can simplify this one. Here that is a minus 1/2, the coefficients, and that's 1 over x, and that will become x to the 3, so that x squared. So here now x is approaching 0 from the right, so that the value must be 0. Okay, and let's consider this one extra. Here now, if you are trying to compare x and e to the x, then you can consider in this way: limit and x approaches infinity, and x over e to the x. Then it's infinite over infinity, so that you can use L'Hopital's rule. So there's 1 over e to the x. Now 1 over infinity, so it will become 0. That means that x and e to the x, and as x approaches infinity, e to the x is approaching infinity much faster than x. So it's growing, e to the x is growing much faster than x, so that the ratio will become 0. And secondly, now limit x approaches infinity, and here now, okay, now logarithm x over x. Okay, so it is infinite over infinity, so we can use L'Hopital's rule. Derivative of logarithm x is 1 over x, and now derivative of x is 1. As x approaches infinity, the top is approaching 0, so that is 0, which means that now in logarithm, okay, x is approaching, growing faster than logarithm x, or logarithm x is growing much slower than x. Pictorially, also we can explain this one. Okay, now here x and y coordinates, and y equal x is the 45-degree straight line y equal x. Now y equal e to the x is increasing much faster than y equal x, and is inverse as y equal logarithm x. So it is a y equal logarithm x. Once x is e to the x is increasing much faster than y equal x, then now is because it's a symmetry with respect to y equal x, and the y equal logarithm x is much slower than y equal x. Right? Geometrically, it's quite clear. Now we'll go to here. Now we'll try to consider another form of the terms, that is infinite minus infinity. Now again, you have to manipulate the given term here. Now once x is approaching 0, then 1 over sine x is approaching infinity, and 1 over x is also approaching infinity. So it is type infinity minus infinity. Now that is, if you try to find the common denominator and try to combine them, then you can do in this way. Limit as x approaches 0, now x sine x, and here we have, that is x minus sine x. Then now x approaches 0, that means that top is approaching 0 and bottom is approaching 0. So that is 0 over 0 shape. So you can use L'Hopital's rule, the same limit, and 1 minus cosine x. By using the product rule, you can get here, that is a sine x, and here plus x cosine x. Now, as x approaches 0, top will approach 0 and bottom will approach 0 simultaneously. So that again, we can apply L'Hopital's rule once more, limit, and that is same as now sine x, and divide by here, that is cosine x. And for this one, and you can make the derivative, you can make a derivative by using product rule. So that is cosine x. And then here, minus x sine x. The derivative of cosine x is minus sine x. Now, for this one, it is approaching 0. Now, bottom is approaching now 2, cosine 0, again one more cosine 0, and that is approaching 0, so that 2, and on the bottom, that means that this is 0. Okay, so here they are approaching infinity and infinity. However, this term and that term, as x approaches 0, and that is basically once one is growing infinity, then the other one is now growing again infinity, but they are growing the same way, so that subtraction becomes 0. Okay, so yeah, if x is approaching from 0 from the right, then that will go to a positive infinity, and again this one will go to infinity, but the manner, increasing manner, is the same, so that the subtraction will become 0. Okay, now for this one, again, once x approaches infinity, then there is infinity, and again infinity. Now for this one, now by using the logarithm law, you can get this one in this way. Limit, and here logarithm, now there is 2x and x plus 1, like that. Then once x approaches infinity, then now this term inside of logarithm is infinite over infinity. But logarithm is a continuous function, so that you can change the limit and logarithm. So that is the same as logarithm, and then here limit and 2x over x plus 1. Okay, now let's try to get that one. Once x approaches infinity, then it's infinite over infinity. So it is the same as limit by using LHopitals rule, and that is 2 over 1. So that is same as 2. So it is eventually the same as logarithm 2. Okay, so that is the final answer. Okay, now we can use LHopitals rule for other type, 1 to the infinity, 0 to the 0, and infinite to the 0. Okay, for those power, basically we'll try to use logarithm technique. Earlier, when we tried to get derivative, and for functions, terms having power, we'll try to use logarithmic differentiation. The same way, once you are dealing with power, then we'll try to use a logarithm technique. Okay, for this example, we'll apply LHopitals rule to show that here 1 plus x and power 1 over x, as x approaches 0 from the right, the value is e. Sometimes e is defined along with that definition. We'll prove it here now. The e, earlier we used the e in this way. Yeah, y equal e to the x as an exponential function such that now y prime at 0 equal 1. The slope at 0 is 1. In this way, we try to find the e. Right? So that is the definition of e. Now, we can define e in this way. Here, 1 plus x. So as x approaches 0, then that is approaching 1. And now that is infinite power. So 1 to the infinity. But for this special form, the limit is e. We can prove it quite easily by using logarithm technique. Okay, rather than that itself, we are here applying logarithm. Then logarithm of fx is the same as now. Okay, logarithm. Okay, logarithm of fx, that's same as logarithm of 1 plus x and 1 over x by using the power law. Oops, that's not 3. Okay, that's x. 1 over x can go out, so that there's 1 over x and logarithm 1 plus x. We can rewrite this one in this way. There's a logarithm 1 plus x and divided by x. Okay. Then here we apply the limit as x approaches 0 from the right. Then now that is approaching 0 and also bottom is approaching 0. So we can use here from here by using the LHopitals rule. We can get here now that is same as 1 over and 1 plus x on the top and bottom, there's 1. Now x is approaching 0, so that the value is 1. Okay. So we, along with that computation, we end up with this one, limit, okay, logarithm f of x is 1. But limit is, the logarithm is continuous function, so that here we can change in this way. There's a logarithm and then limit. Okay, we'll write down the detail. X approaches 0 plus and f of x. That one is 1. And here, that must be e, so that logarithm, natural logarithm e is 1. Right? So eventually, we prove that limit of fx equal e. Okay, we reached this one. Now, we can consider that or you are applying exponential function both sides. Then now limit of fx is coming out, and then now logarithm will disappear, and right hand side e to the 1, which is e. You can do this way. Either way, you can find here the quantity. Okay. Now for this one, fx is now x to the 1 over x. So here, if you consider logarithm of fx, then there is a logarithm of x to the 1 over x. So that is same as here 1 over x and logarithm x. We can rewrite this one in this way, logarithm x over x. Now we apply limit. Okay, here the limit, and last moment here limit as x approaches infinity. Then now that is infinity over infinite shape. So that is same as limit, and the derivative is 1 over x and derivative is 1. X approaches infinity, so that the value is 0. That means that here limit and logarithm of fx equal 0, but now the left hand side can be written in this way. Here a logarithm, and we can change the limit and logarithm. So the limit, okay, and f of x, that is 0, right? That means that here that term must be 1, right? So the answer for this one is 1. That is the final answer. In this way, you can find it. So once power is related, then rather than the given term itself, you may try to get the limit of the logarithm of the given term. Then you can figure out the quantity after getting the limit. Okay? Okay, this is end of the section. Thank you.